So the plan for today is to wrap up the material that's going to be on next week's exam. So we've got an exam a week from Wednesday, and that's going to cover material in chapters 1 and 2 of the book that we've done. So it'll cover everything we've done with first and second order differential equations. So today I want to focus on the work we've done with second order differential equations and how those types of differential equations have applications in mechanics. In particular, we'll look at mass spring systems. So before we get started, are there any general questions I can help with? Just so you guys are aware, we've got our exam is next week. So on next Monday, there's not going to be a homework assignment due like you have every Monday, since next week is an exam. So instead, later on this week, I'll put up some practice problems for the exam that you can practice over the weekend getting ready for the exam. And those are not going to be collected, but that's something that we can talk about next week. A week from today, on Monday next week, we'll just spend the time reviewing for the exam that's on Wednesday. So I'll put up some review materials if you want to look at them before we meet on Monday. That might be a good idea. Okay, questions about that?
Are you gonna post the solutions for those anywhere?
Yes. So yeah, as of now, the solutions for the first 3 homeworks are up. I will post the solutions for the 4th assignment that you guys handed in last week up. I'll put the solutions for the stuff that you handed in this week up later on this week. I will put practice problems and I will put solutions to those practice problems up also. Yeah.
Thank you.
Okay, so let's wrap up this material. And I should also say that on Wednesday's class, we're going to cover some new stuff on systems of differential equations. So we'll start an introduction into chapter 3, but that material won't be on the exam. Okay, so that'll just give us a little introduction for what we'll start covering after the exam. Okay, so let's consider these mass spring problems. And today we'll take a look at maybe a couple of instances where these things are actually applied. And so with these mass spring systems, we have 3 parameters that determine the motion here. And so just recall these systems. And in case you're wondering what we're working with, we're on worksheet 13. And that is called like mass spring, I think is the name of the document. And so in general, these differential equations are mass times the acceleration plus the friction constant times the velocity plus the spring constant times our position. And if we don't have any forcing in the system, then it's going to equal 0. And that's kind of what we'll start working with first. And then we can start to think about what happens when we start to force things. Okay, and so over here, again, is the mass. This part comes from the friction of the surface. And this part is related to the stiffness of the spring. And so when this term B, first of all, we're assuming that these constants are positive. And when B is equal to 0, we call that the undamped motion. Here we'll consider the case when we do have damping. So in this case, our differential equation would be, we're told that the mass is 2 and the damping constant is 1. So we've got a 1 times y prime. And then we've got a spring constant of 3. And we'll assume that we don't have any other external forces. So that would be our system that would govern the motion of such a mass spring system. And so if we want to solve this system, what's one technique that we can use to solve this?
quadratic formula?
Yeah, so we'll use the characteristic equation type of approach. So from this, we can set up our corresponding characteristic equations. We would have 2r squared plus 1 times r plus 3 is equal to 0. And we could try and factor this. It's not going to factor cleanly. We actually have complex roots here. So in order to figure out these roots, let's use the quadratic formula. So we've got minus our value for b is 1, plus or minus the square root of 1 squared minus for a c, which is 24 all over 2 times a, which would be 2 times 2. So our roots here are minus 1/4 plus or minus the square root of 23 over 4i, if we simplify that. So under the square root, right, we have the square root of minus 23. All right, any questions about that?
Is there a reason why you wouldn't want to get rid of the coefficient in front of the y double prime term?
You mean like divide everything by 2 from the get-go? You could, yeah, that's not gonna, you get the same result in the end anyway. Because if I divide by 2, I need to divide all of the coefficients by 2. And so I'll just say in the end, you would get a consistent answer. So yeah, you're allowed to do that in this case because you have a homogeneous right side equal to 0. If that right side were not equal to 0, well, it wouldn't affect finding the homogeneous solution yet. You could divide by 2. I don't think it's too nice here because you know, these terms are not even, so then you would have fractions in here. Yeah. Okay. Any other questions about how we got those roots? And then so from this, we could get our general solution, which would be like C1 e to the minus t over 4 C2 e to the minus t over 4 times the sine of the same thing. Okay, questions? And so when we have solutions like this, which case are we in? Is this underdamped, overdamped, or critically damped?
Underdamped.
Okay, and why is this underdamped? That's right.
As we allow t to go to 0, it's just going to infinitely approach 0 closer and closer.
Yeah, so that's for these mass spring systems, yeah, sometimes when they're undamped, they're just going to keep on, you know, oscillating indefinitely. When we add some damping, it's going to head to 0, but there's different ways that you could approach 0. So you can start with some initial position, say over here, and then let go of the spring, and it's possible it could do something like this. Okay, and what this would mean is that the spring is stretched out, it compresses in, and then it slowly goes back to its equilibrium. And so it never oscillates, it never goes back past its equilibrium and so on. So when we have this, which is no oscillations, remember this is the over damped situation. So the spring is just gonna move, head back in the other direction maybe, and then just settle back towards equilibrium, and it's not gonna have any rocking. When we have situations like this, where we have these trig solutions, right, this would be an example of an underdamped situation. And that's because this one does oscillate. And so these solutions, maybe we start over here, they are going to oscillate. It's just that the amplitude is going to head towards 0 as time goes on. So it's kind of this term over here is giving us our amplitude. Which is going to head towards 0 as t heads towards infinity. So one thing that's nice about this mass spring system is that we can connect kind of the behavior of the mass to the different behaviors, to the different types of roots of the characteristic equation that we've seen.
What does that say? 0 cosine of t?
The where you mean over
Or
here?
0 as t, the red, yeah.
This is telling us that the amplitude is going to 0 as time goes to infinity. So that would be like these distances over here are heading towards 0. So each time the mass goes, it's kind of going a little bit less and a little bit less, and it's just going to slowly rock back to its equilibrium.
Thank you.
Yep. Okay. Any other questions about that? Let me bypass C for a second, and let's just keep on thinking about the different properties that our solution has over here. So one property is we've talked about the fact that its amplitude is getting smaller and smaller and smaller. The other thing that might be interesting with these sorts of motions is how long does it take this mass to do one cycle, meaning go from its furthest point to its closest point and then back to its furthest point or something like that. And so here we would consider one period of this to be how long does it take to go from its maximum and then reach its next maximum point. Okay, what's happening here is because the amplitude is decreasing, they're getting smaller and smaller, but we would still consider one period to be the amount of time does it take to go from its furthest position, smushed in, back to its furthest position. And so from trig, hopefully you can recall that the period is equal to 2 pi divided by that term that we'll denote with an omega. So just note that this sort of W looking symbol that you've been seeing in the book, if you've been reading this, is an omega. So in this case, our period would be the 2 pi over the square root of 23 all divided by 4. And one thing to just know is that this is what happens when we do problems in the real world, is that these numbers don't necessarily work out beautifully. Okay. Any questions so far?
What'd you say the W was again? Like, what's the
Yeah. So this W, we'll call it an omega here. It's a Greek letter, and it's equal this term that's in front of the multiple that's in front of the t inside of our homogeneous solution. So in this case, that's that root 23 over 4.
But in terms of like the period is equal to 2 pi divided by still just omega?
The period is 2 pi divided by the absolute value of omega. Yeah. Sometimes that might be negative. A period should be a positive number, so that's why we just take the absolute value. And so here, if I approximate this, since this number probably doesn't mean too much to us, okay, we would say this period, if you approximate that, comes out to about 5.24 seconds. So this tells us how long does it take to go from this maximum point away and then all of a sudden complete one cycle, which means go past the equilibrium to the other side and then reach back over here. So this takes about 5.24 seconds to do. So that's what we would call the period of this motion And some terms that you might have seen in the textbook that then we can talk about the frequency which is 1 over the period, which in this case would be 1 divided by the 5.24 seconds. And that winds up being, in this case, about 0.19. And this, the period tells us how many seconds does it take to do one cycle. The frequency tells us kind of the opposite of that. It tells us how many cycles are we going to complete in 1 second. So in this case, our frequency would be 0.19 cycles per second. Let me just say that has a unit which is often called hertz, cycles per second. So if you were reading the book and you've seen different terms like omega and period and frequency, these are all related to each other, but they're kind of describing the how fast this thing is bobbing back and forth in slightly different terms. So this term, if you were reading, this omega over here is what's called the angular frequency. And this would be what is called like the natural frequency. And so more commonly, we describe it in terms of how many cycles are completed in a second. Okay, any questions so far about this example? So kind of just so far, we found like the homogeneous solution. We saw that this thing is going to bounce back and forth, but it will slowly settle back towards its equilibrium. And we can describe how fast it's cycling back and forth as well. And this is not going to change as time goes on. The period stays the same. That might not be reflected in my picture, but the period is going to stay the same. It's just the amplitude is getting smaller and smaller. Okay, and then the last thing that we haven't talked about here is this question C, which is saying, what is the value of B that would make this system critically damped? And so critically damped means it's this very special value where the system suddenly changes from oscillating like ours does over here to not oscillating anymore. So it's kind of this critical value of B. It's like the minimal amount of friction which is going to cause this system not to oscillate. Let me get some more space. Okay, so so critically damped is going to be the case when the value of the friction or the damping coefficient okay, that's going to change this system from over to underdamped. And so this is the case where we have one repeated real root. So just to kind of generalize things, right? We have underdamping when we have complex roots, like in the previous one. We have overdamping when we have real roots. And so critically damped is the case where we have that repeated real root. And so that means we had a system which was, we had a mass which was 2. We're going to let the damping coefficient vary a little bit, but we'll fix in the spring constant and the mass.
Adam,
Yeah.
can you just clarify exactly what one repeated real root means again? I think I understand it. I just want to be sure. Like,
Yeah, so that means when you've got a quadratic equation, oops. You can either have two distinct real roots. That's like when your quadratic looks like this, for example. You have two repeated real roots. You could have one repeated real root. And that's what happens when your quadratic has a vertex on the axis, or you could have no real roots. And that might be something that looks like this, that never crosses that axis. And so we've talked about each of these scenarios and how based on the roots, we get different forms for the general solution. So when we have two distinct real roots, it looks like this. When we have one repeated real root, it looked like that. And then when we had the no real roots, that's when we had Euler's formula and the e's and the sines and cosines and all that. So what is going to determine whether we have real, distinct, real repeated, or complex roots is going to be what we call the discriminant when we're calculating the roots using the quadratic formula. So here are characteristic equation is 2r squared plus br plus 3, where b is now an undetermined coefficient. And if we wanted to find the roots, we would take minus b plus or minus square root of b squared minus 4ac all over 2a. And so this expression that's underneath the square root, this is called the discriminant. And so when the discriminant when this thing is positive, that means the thing under the square root is defined and we'll get two real roots. When this is less than 0, that means we're going to have something negative under the square root and we get complex roots. And so the critically damped case is going to be when we get 0 for the discriminant. So in this case, we don't know what B is, but we know that A is 2, and we're told that C, or in this case, K is 3. So we've got an equation. We want the thing under the square root to be equal to 0. So that would be B squared minus 24 should be 0. So that tells me that this coefficient B, right, it should be technically plus or minus the square root of 24, but because these coefficients are always positive, if we have a damping coefficient that is equal to the square root of 24, that's the point where suddenly we now have put in enough damping that the solution is not going to oscillate anymore. So in other words, this is the minimum amount of damping in which you would not have any oscillations.
And for it to be no oscillation, does that mean it just doesn't go back past the equilibrium point? Or?
Say that again, Brian, sorry.
So for no oscillations, that means it doesn't go back past the equilibrium. Like once it goes across it the first time, it doesn't go back past it.
It might, yeah, so be careful. And that doesn't necessarily depend on the damping, but yeah, you could have a situation where your mass goes like this and then just heads back and never crosses over the equilibrium. So remember that this y, when we're crossing this axis, right, that's when we're at our equilibrium. So it could do this. It could do this as well. And I'll just say both of these situations would be cases where we have no oscillation because we never go back past the equilibrium. So both of these cases would be considered no oscillations, and it's not necessarily an issue of the damping necessarily, because you could put a whole lot of initial velocity on this thing to cause it to go down this way over here. It's just that the damping won't let it pass back over the equilibrium. So as far as whether it does this over here or whether it does this over here, does depend on the damping in addition to the initial conditions as well. So it might do this, it might do this. It definitely won't do this over here when we have critically damped. Any other questions? Okay, so just a couple of things to clear up, since we haven't been too careful about the units that we've been using in these problems, that I would like to be more careful with when we look at the other examples, and that is we'll be using the metric system for these. So that means we're gonna be measuring our force in newtons as opposed to like foot-pounds. So we'll denote force with newtons, and we'll denote that with an N. And so this spring constant K is really telling you how much force do you need to put on this mass in order to move it 1 meter. So it has units of newtons per meter. So it means every time you need to move this spring 1 meter, this is how much force you need to put on it. So it has units of Newton meters, and the damping constant is what we call a unit of impulse. And so it has units Newton seconds per meter. And so we're typically going to measure mass in metrics like kilograms or grams, and we'll measure distance using the metric system. We'll use meters for that as well. Okay, so let's see. So question 2 kind of deals with how we measure things. Right? This is how we measure weights. You go to the grocery store, you've got some fruit, you put them in a little basket. I don't know if they still have these things these days, and there's a spring, it pulls the spring down, right, and we get a measurement. All of that is using these mass spring systems. We can measure based on how big the displacement of this spring is. We can then measure what's the mass that's being applied to that spring. So we'll kind of think about it like this, where we've got a spring and we're kind of balancing a mass like this, and it's very much the same problem if you invert it and hang it the other way. And then we're going to look at how this spring behaves, and that's going to tell us something about the mass that we put on top of that spring. So we're going to ignore damping here, which is going to make the problem a lot nicer. So we don't have any friction term in here. All we have is the motion of this system is going to depend on how much mass do we put on top of the spring and how much force does it take to push this spring down in general. So let's say we don't know what the mass is. That's usually the case. But we do know about properties of this spring. And so we can oftentimes figure out what is the spring constant. So let's say in this case, it's 4 newtons per meter. So if I want to move this spring 1 meter, I have to apply 4 newtons worth of force on it. So essentially what we're trying to get here is to figure out what is the mass of this object if we know how the spring is bobbing up and down. And if we ignore friction, then this spring would bob up and down forever. So you can imagine this spring, being in some sort of a vacuum. Okay, so we don't have air resistance, we don't have gravity going on in here either. Okay, so part A, it's asking us to solve this equation where we now have a value for K, which is 4. So we want to find the general solution, and this will depend on the mass M. And then in part B, we're told that if the frequency which recall is equal to 1 over the period, if that is equal to 0.8 cycles per second, then we want to figure out what is the mass M for this model. Okay, so finding the general solution. I guess first thing is any questions about what this problem is asking us so far? Okay, so for part A, how could we figure out what the general solution to this is?
Could we make the my double prime plus 4y equals 0 mr squared plus 4y? Or plus 4, sorry, equals 0? Plus 4.
Plus 4, yeah. And that y means, right, that's the constant term. So that is a characteristic equation. That's right. And this means that our roots, we would have r squared is equal to minus 4 over m. And so r would be plus or minus 2 over the square root of mi, taking the square root of the minus 4. So this tells us our general solution. Since we don't have any initial conditions, we'll just say that we've got C1, and since these are purely imaginary, right, we're dealing with the undamped case, we're going to get trig functions whose amplitudes are the same for all time. So this, because there's no damping, friction isn't going to slow this motion down. So we've got 2 over the square root of m t plus c2 times the sine of 2 over root m t. okay, where m is now just denoting the mass of this object. And so let me just say that this property of the system is what's called the natural frequency. And then we'll see that this is important to identify if you are going to add some forcing to this system, to make a note of this so that you don't get resonance, so that your mechanical system does not fall to pieces. Okay, so we've got the general solution in A. Any questions where we found that from? And so this, who knows what it's going to look like, but it would look, sorry, would just look like a trig function, okay, where the amplitude is not changing, the frequency is not changing for all time. So any thoughts about how we can use this information in B to figure out what M should be?
Our radial frequency is going to be 2 over square root of m, which we know is going to be equal to 2 pi f.
Okay, so what's the equation that you're setting up here, Kyle? I think you have an equation in that statement somewhere.
The radial frequency, W, is equal to 2 over square root of m.
Mm-hmm.
And we know that the radial frequency is the equivalent of 2 pi f, or 2 pi over t, which is the period.
Yeah, so so we've got this term over here, and just so the terminology is okay, this is right what we would call the angular velocity, or the angular frequency. Right, and then from this, just different ways that you might want to think about this, right, is from this you could then think about the period, which is saying how long does it take to do one cycle. So that would be the period is going to be 2 pi over the absolute value of this. So that would give us, the 2's cancel. I think we would just get a pi times omega, right? I don't know where that came from. I think square root of m, right?
Yeah, it's the square root of m.
Yeah, thanks. Just simplifying 2 pi over 2 over square root of m. Yeah, so the 2's cancel, we got a pi, we've got square root of m. And so the frequency here would be 1 over this. And we know that that should equal 0.8. And from this, we can calculate the mass, and we get the mass for this one.
I got 0.6307 kilograms.
If you got some, please, you're welcome to chime in your answers or text them in as well. Thanks, Kyle, for sharing that one.
I got 100 divided by 64 pi. But that probably is wrong.
Yeah, so I'm getting something that a couple of other people are chatting in. So I got 0.158 kilograms if you were to solve for the mass here. And so solving for the mass, bring that over there, bring that over there. I think you would actually have like 1 over pi times 0.8 squared. And I think that winds up being 0.158 kilograms. So that's kind of neat. I mean, this is a very old mechanics using springs, but I think you'd be hard pressed to find any many mechanical devices that don't have some spring in them somewhere along the way. The forces that are acting on that spring are very much governed by the types of differential equations we've been studying. Any questions? Okay, so I think I will bypass this one for now. And so this is very much sort of using the same sort of ideas in question 2. And the idea here is when you've got train tracks, I'm going to try and draw something. Oftentimes, when the track just ends, they put a bumper there because they don't want the train to just keep on going. And so there'll be some sort of bumpery thing over here. And inside this bumper, it's called a cushion, is a little spring. So when the railroad hits the spring, as long as it's not going crazy fast, that spring will compress and slow it down. If the railroad car is going too fast, then that spring is not going to stop it, and it's just going to slam right through it. So this problem takes a look at the properties of that spring, how fast, and now you need to consider some initial conditions. How fast is the rail car going? What is its maximum speed if the spring is allowed to absorb such amount of force? So I'll leave that one for you to think about. Maybe we'll have time to talk about it together, but I want to take a look at least one forced oscillation problem. So now this is going to connect what we've been doing with the behavior of the free mass spring system, and now we're going to put some force on it. And so the picture here is we have a water tower, and if anyone's seen water towers, even like these little ones that sit on top of apartment buildings, they all have some sort of like meshing that goes around, right? And so the support system that they put on the base has a sort of natural frequency. It operates like a spring in some sense. It's just a very, very strong, stiff spring, but it does give. And so it does have some natural frequency to it. So the idea here is, well, what's the maximum amount of external force? And we'll think about that force as an earthquake here, that this water tower could sustain and without tipping over. And so we're given some information. So we're going to think about the water tower itself as just the big mass. And again, we're going to think about the support system as the spring that it's set up on top of. And we're going to ignore any friction here. And usually that's okay. Friction is kind of the least significant of the forces involved here. And so usually that doesn't impact things too much. But if you wanted to consider friction, you could certainly add that back in. So if we ignore friction, then we're working with this model. And we're told the mass is 10,000 kilograms. And we're also told that it takes a force of 1,000 newtons to move this container 1 meter. Okay, so in other words, if you wanted to push this container down by 1 meter, you would have to put 1,000 newtons worth of pressure on top of it.
It is that K?
That is K, exactly. Yep, so K is actually, when we talk about this spring constant, it's actually telling us how much force do you need to put on the spring to move it 1 meter. Yeah, so, right, the kind of point I wanna make here is that is when we wanna kind of take these techniques and apply them to these contexts, things are not always going to be stated in terms of M equals this, K equals that, etc. You kind of need to read the problem, pick up what information you're given. So now we know that we've got a mass, 10,000 kilograms. That's right. And this 1,000 newtons to move it 1 meter means K is 1,000 newtons per meter. And let's first assume that we don't have any force. It's a nice quiet day. There's no earthquake. There's not much wind. And so there's no other external forces acting on this mass besides the spring, besides the base, which is holding it up. So why don't you go ahead and solve this differential equation and figure out what the frequency of the homogeneous system is. Call this like the natural frequency. Okay, and so here we are working with an undamped one. So you should expect to get these complex solutions where the real part is 0 here. So you get these sum of a sine and a cosine. Right, so for these undamped ones, hopefully it makes sense that you are expecting to get something that looks like this. And this value, omega, I'll call it omega naught, is what we call like the natural frequency of this system. Yeah, is there a question?
Yeah. So
Yep.
for this one, we just pretty much do the same thing we did for 2, right?
Yeah. That's right. Find the characteristic equation, etc. Yep. Anyone get a value for omega?
I got the square root of 10 over 10.
The square root of 10 over 10?
Yeah.
Square root of 1, you mean?
1 over 10.
Oh yeah, sorry. Yes.
Square root of 1 over 10. Yeah. That's right. And so in general, if you're reading the book, right, they tell you that when you have an undamped system, when you don't have an undamped system, this is not the case, but if you have an undamped system, then this is going to equal the square root of k over n. So there is some relation to the stiffness of the spring and the mass. So that 1 over 10 came from K over M, yeah. And then we take the square root. And so if we round that off, that's like 0.3162 or something like that. And I think for these cases, it's actually, I think, more useful to write these things as decimals than leave them in their perfect form, because it's kind of hard to imagine what is the value of the square root of 1/10. So for this one, yeah, we've got y is equal to C1 cosine of 0.3162t plus C2 times the sine of the same. So this omega naught, this is like what is our natural angular frequency of these cycles. So usually what we'd like to describe this frequency is not in terms of the angular frequency, but in terms of how many cycles do you do per second. So in absence of any other forces, how can we use these solutions that we found above right here to figure out how many cycles does this go through in a second?
Then you said the period is 2 pi over 0.316, right?
Yeah, so we can find the period, which is going to be 2 pi over the absolute value of that term.
And then just take the inverse of that?
Yeah, so we can say like the cycles per second this is what we call kind of the usual frequency. Would therefore be 1 over the period. So we can take that kind of angular frequency that we had, which was the 0.3162, and just divide it by 2 pi and convert it to what we call the usual frequency. And I think that is like 0.05 cycles per second. Well, any questions? And so this is important to note here because if you get an earthquake, okay, even if it's not a strong one, that happens to have like the perfect frequency that matches the setup of this water tower, and you have resonance, that's when this thing might get wiped out. So it's not even necessarily, certainly like having a really large earthquake would cause just about any structure to fall down, but there's also kind of these very special frequencies that things can fall apart even if the external force is not huge, just when it's like just right. So that would be the natural frequency for this system. And so in part B, now what we want to figure out is, okay, is this water tower going to be able to sustain an earthquake whose frequency is 0.5 cycles per second? I think that's what's going on in part B. And so kind of the key thing here is if this water tower moves more than 1.5 meters from its resting position, that's going to be a problem. So now we've got a forcing function. So we've got an earthquake, and it's going to put some external force on it. So we'll just label that subscript with EXT. And we're told that this external force is equal to the mass of the system, of the container, times omega squared cosine omega t. Where for our case, we're dealing with a mass of 10,000 kilograms. And we're told that the cycles per second okay, and that's so. And so again, what we're told is if the container that if the container moves more than 1.5 meters or more, it's going to collapse. Okay, so and what we found so far was the homogeneous solution, which was C1 cosine of, what do we have? And now we want to think about, well, what happens if now we have some forcing? So in addition to just the water moving up and down, we now put an earthquake, which causes the support of it also to move up and down. And so we want to find the particular solution if we have a forcing function which was m omega squared cosine of omega t. Okay, so any thoughts about what we can do from here?
You could find omega.
Yeah, let's find omega. Yeah, that's right. So we know that the mass is 10,000 kilograms, and we want to find omega. And what we know is that the frequency, right, which is 1 over the period, is 0.5 cycles per second. And so from this, we should be able to find omega, right? Because the period 2 pi over the absolute value of omega. So why don't you go ahead and try and figure out what the value of omega should be for this one. And if you've got it, chat it in to me once you've got it. Okay, anybody else? We've got 2 votes for pi so far. Okay, so we've got several votes for pi coming in here. And so, yeah, so we've got the frequency is 0.5, and so that should equal 1 over the period. And so,
Isn't it 0.05?
so that was for the natural frequency of the system was 0.05. In this case, we're told that, so that's relating to the makeup of the water tower, but here we're told an earthquake comes and it has a different frequency. So its frequency was 0.5. So the 0.5 came from this given info over here. Yeah, so we were trying to figure out what omega is, and so we can use the fact that we have 0.5 should equal 1 over the period. So that should equal the absolute value of omega over 2 pi. And so solving for omega, we would get exactly that omega is pi. That's right. So that means we've got 10,000 pi squared times the cosine of pi t. And again, the task was we wanted to figure out what is the particular solution for this forcing function. And now we found out, given the mass and the frequency of the earthquake, exactly what the forcing function for the earthquake looks like. And we want to find the particular solution here. So any thoughts about what a good guess would be for this particular solution based on what we're looking at over here?
A cosine pi t plus b sine pi t?
Yeah, so this is a cosine function, right? Where the term inside the cosine is pi. So we're going to guess something similar. But just remember, when we are dealing with these trig functions, we might need to account for both the cosine piece and a sine piece. So our guess would look something like this. We compare it to the homogeneous solution that we found over here. And we can see that there's no resonance since this stuff over here is not the same frequency that we have with our earthquake, right? So that's good. At least we don't have resonance there. That would cause it to crumble. But this is going to cause it to sway still. And the question is it going to sway beyond our catastrophe point? So then at this point, we would take this and plug it into the differential equation and figure out what the coefficients A and B would need to be. So, right, we would take this, plug it in for Y, just to kind of go through what you would want to do. You'd want to find the first and second derivative of this and plug that in over there. Plug this in over here, and then match up your coefficients so that on the right side you have this, and you also will have some sign terms to account for. So you'll get some equation that A's and B's need to satisfy to give me the appropriate term over here. And then you'll have another equation that A and B need to satisfy so that the sign term cancels out. But let's do it. We got 10 minutes. That seems about right. So why don't I'll let you work on it for about 5 minutes, and then we'll take the last 5 minutes just to check in with each other to see how it went. So we're back over here where we had, here was the parameters of the system based on the mass and the tower. And then we had our earthquake on this side, the forcing function on the right. And so we wanted to find a particular solution for this differential equation. And because we have a cosine pi t over here, we're going to guess cosine pi t plus a sine pi t option. So now we take the derivative. Each time we take a derivative, a pi should come out front. We don't really need the first derivative beyond just getting the second derivative. So we have a second derivative should be minus pi squared a cosine pi t minus pi squared b sine of pi t. So now I take this and I plug it in over here. I take y, I plug it in over here, and I group the terms. So this stuff over here is the 10,000 times the second derivative, and then we're going to add to that 1,000 times the original function y. And when you do that, you can group the cosines and the sine terms together. So I have two cosine terms grouped together. I have two sine terms grouped together. And recall that our forcing function for the earthquake, it did not have any sine term. And it did have a cosine term that I think was a 10,000 pi squared cosine pi t. So then this tells us we have two equations. For the cosine piece, I need these coefficients in front of the cosine, which is the minus 10,000 pi squared a plus 1,000 a. That should give me the 10,000 pi squared. And as far as the b terms go, all of this stuff over here should equal 0. So from this equation over here, I can see that the only way that's going to happen is if b is equal to 0. And from this equation over here, I suppose we can get a very complicated looking expression for a, which is 10,000 pi squared, all divided by 1,000 minus 10,000 pi squared. Did anybody get this and simplify it? I don't have a calculator here, so I'm just kind of.
You could take a 10 out, so it'd be 10 pi squared, 1 minus 10 pi squared.
Yeah, and so all of this just should simplify to a decimal. I don't need it to.
I got negative 1.01, and I think that sounds right. It looks right, kind of.
So you got minus 1.01. Anybody get something close to that? We got a thumbs up. Okay. Yeah. So we get the value for A, and we got that B is 0. So we get a particular solution that is,
I got negative 1.1.
it might be a rounding issue. Yeah. I'll calculate this more carefully when I put the solutions up, but I think it should be somewhere around there. Yeah. If you're getting something a little bit off, it might be a rounding issue. Yeah, and so this would give us the particular solution here. And let me just say that if we start with the tower at rest, so in other words, y of 0 is 0, y prime of 0 is also equal to 0, well, that would mean that the homogeneous solution would be 0. And the only component that's adding anything to the motion here is this particular solution due to the earthquake, right? So you can imagine if there was no earthquake, as time goes on, that tower would just sit there and not move at all. But once you give it some force, even if it's starting at rest, then just to kind of give you the quick story here, the fact that it starts off at rest means that the homogeneous solution would be 0, that this constant C1 and C2 in the homogeneous solution should both be 0. And that would tell me that the solution to this is just going to be given by the particular solution. And this tells me, well, that's actually plus. What the amplitude of this is. And we said that we're going to get a collapse if it moves more than 1.25 meters. And we can see here that we're safe. It's not going to move more. So at most, it's going to move a little bit more than a meter, but it won't move as far as 1.5 meters. So this tells us that the water tower in this case would be safe. It is going to remain standing since we're not going to hit this displacement of more than 1.5 meters. Okay, I'm sorry. We ran a little bit over today, so I will stop here. So this certainly goes beyond the problem that you guys have on your homework relating to this. So you do have a mass spring system that's a bit simpler than this one, but I did want to take it a little bit further just to see how these ideas are actually applied in practice. And I'll just say that, you know, depending on how you construct your tower, you can certainly account for certain types of resonance. Okay, so I will stop here. If you have any questions about this or anything else, just let me know. Otherwise, I will see everybody on Wednesday, and on Wednesday we'll start taking a look at systems of differential equations. So I will put up a really short reading quiz for you guys later today to do before Wednesday's class. Otherwise, you've got your homework assignment due tonight, so don't forget about that. And I will see everybody on Wednesday, unless you have some questions and you stop by tomorrow.